All right, let's get started again. I'd like to welcome Daniel and Timur from Valve, talking about Radv. Are we there yet?
Hi, my name is Timur, and this is my colleague Daniel. We are contractors for Valve, and we're here to talk to you about Radv. And first, I'd like to start with what's our mission? Like, why are we doing whatever we're doing? And well, to summarize up simply, we say our mission is to improve the Linux gaming experience. So basically, our job is to do whatever it takes to make Linux a viable platform for gaming. And what exactly is Radv? For those of you who don't know, Radv is a Vulkan driver for AMD Radeon GPUs. And the ACO is the shader compiler backend that Radv uses. It's independently developed in Mesa by mostly the same group. And a little bit of info of when can you use Radv, or what do you need to use it? So initially when they started, they developed it on volcanic islands GPUs. Later they added support for older and newer GPUs. And with Vulkan support, we support Vulkan 1.4 or almost all GPUs, and we support 1.3 for the oldest ones. And of course, we try to support every optional feature that is supported by the current hardware. So Daniel, do you want to talk to us a little bit about the history of the project?
Yeah, hi. Let's have a look at where we started to see how we got where we currently are. Sorry, that's a lot of text. So in June 2016, Bas and Dave got a little bit annoyed that AMD VLK still wasn't open sourced. So they took matters in their own hands and started developing a Vulkan driver for Radeon hardware. And only a few months later, this driver, Radv, got merged into Mesa. And then development really kicked off. So at just a few months later, Samuel was the first person who got contracted to work full-time on Radv. And at this point, I would say, over the next year, Radv was basically an average open source driver. You know, a few bugs here and there. Some games work, or most games work, some don't. Performance, like average, a bit less than average maybe. So like many open source drivers are, to be fair. And so then I joined a year later when it already improved a lot. Because having full-time developers is really something that can drive these developments. I mean, of course, if you spend more time, then you get more. When I joined, LLVM was still the backend compiler for Radv. So Radv translated NIR to LVM-IR, and that caused a lot of issues for us because LLVM follows its own release cycle. And by doing so, you basically, if there's a bug in the compiler, then you have to wait for the next LVM release until it gets final fixed, or you have to carry workarounds in the driver. So other drivers, like AMD VLK, for example, they then just ship their own version of LLVM to get around this issue. This wasn't really an option for us. And also, we were a bit unsatisfied with the performance of LLVM back then. So this to be honest, this changed quite a lot since then. It still has quite slow compile times, but back then also the runtime performance or the generated code wasn't really at the level that we would have liked. So we decided to write our own compiler backend. And 2 months after I joined the team, I started working on that together with Bas. And then later in September, when Reese joined, together with Reese. And yeah, this took quite a lot of time until the next summer, until we actually announced this backend. So this was a lot more effort than anticipated. Then at that time also Timur joined the team. And before Echo got eventually merged into Mesa, just as a single huge commit, because we had not really maintained history. So over the next year, a lot of bugs got ironed out, and when the performance was to our was satisfying, we enabled Echo by default for Radv. Over the course of the next years, we had a few more team members joining us. Georg, who also mainly works on the compiler side, and then we also have Konstantin and Natalie now in the team. I say mostly working on ray tracing, and Konstantin also a lot on other things. I mean, they all work like in many areas. So and since December 2024, Echo is now also the default in RadeonSI for the GCN generations. And of course, there's a lot of other people who contributed to this effort, some of which directly involved with Radv, at least for some time. Others working on infrastructure like CI or other components which are used by Echo directly or indirectly. So thanks to these guys as well. And now I hand it over to Timur again to tell us what is new in the driver.
So it's been a long time since we last had an XDC talk about Radv, and there's been a lot of new developments. But maybe the most important thing is that these days when a new hardware comes out, most of the time we're able to support it on day one, which means if you go to the shop, you buy the best video card you can find, you plug it into your computer, of course your Linux computer, you turn it on, it just works. So huge thanks to AMD for helping us with that. So over the last couple of years, we added support for a lot of new hardware. There is still some, like CDNA, which are not quite there, but we're getting some contributions from the community. And the other thing is that not only we have day one support for the new graphics cards, we also have day one support for most new Vulkan extensions. That's because many of our developers are participating directly in Kronos, which means when they are cooking up a new Vulkan extension, we are there, we can comment on, can we implement this, can we make it more efficient, and usually by the time the extension actually comes out officially from Kronos, we already have a branch somewhere with Radv support, which of course we merge really quickly. So here are a few examples of Vulkan features that we started supporting in the past couple of years. I'm not going to go through all of them in detail because then you guys would have to sit here with us for the whole day. But a few of them that are important to us are the CPU overhead, which are spearheaded by Mike. He wrote actually a test suite just to test the overhead for us. The other thing that we're trying to do is combat the stutter caused by shader compilation. So in the very early days, some of us wrote fossilize. Thank you, Hans Christian, for that. Later on, for the driver side, we wrote a new compiler backend to kind of speed up the compilation, but we realized, well, that's still not enough. There is still stuttering, even if you compile everything super quickly. So then we went down and changed the API to kind of give game developers or translation layer developers the opportunity to do it faster. And of course, one of the coolest latest features is ray tracing. We added a lot of new stuff. Well, mostly Konstantin and Natalie did. So we now have some acceleration structure builds which are shared with other drivers. We are conformant with the spec, which is very important. And most games that are ray traced, they work out of the box. So basically, not only can you buy the latest card, plug it in, it will work, but it will also run your ray tracing games. Another important one is the so-called device-generated commands, which is very useful for GPU-driven rendering. So this means, in a nutshell, that your draw calls are not generated on the CPU anymore, but rather on the GPU. So that frees up the CPU to do other things for you. And this one was actually very important for API translation. And I just want to say a few words about how we test this. So we have Mesa CI for Radv, thanks to Martin, who is working tirelessly on that. And thanks to his efforts, now we have CI coverage for all GPU generations. So basically, literally every single AMD generation now has a CI runner. And if we have some changes in the driver, we can run tests on all of them at the same time, see if it works. If not, we can fix it. We have pre-merge testing, of course, on the latest ones, post-merge on everything else, just because we just don't have like all the hardware in the world to do everything pre-merge. And another important thing that we've been working on lately is trying to share code with other drivers. So the most obvious choice for that is the other AMD driver in the tree, which is RadeonSI, the OpenGL driver. So in order to do that, we actually have a lot of common code that we are actively working on, in addition to our own driver-specific code. It's again, the devil is in the details, and there is too much of that to go through everything. But here are kind of the keywords for everybody who actually wants to dig into it. And what's new in the compiler, Daniel?
Yeah, also the compiler didn't stand still, so there was a lot of new development. And so one of the bigger things was the decoupling from Vulkan. So Timur already mentioned that we now try to share a lot of code between RadeonSI and and Radv, but when it comes to the compiler, that is basically a whole different beast. So when we first developed Echo, it was supposed to be the compiler backend for Radv. So what did we do? Well, basically just include half of Radv into the compiler, because, well, we have to transfer some information from the driver to the compiler to emit the correct code. But then when you want to support a different API or different driver front end, then yeah, this isn't particularly useful to have like one driver included in the compiler. So we had to disentangle all of Radv from Echo, and this was quite a major task. So thanks to Kiang, who did a lot of this work. And now RadeonSI can also use Echo as compiler backend. Yeah, besides that, of course, new hardware support is also like always a task. This is never standing still, because there's new releases every year or every other year. So as of now, Echo supports all GPU generations from the earliest GCN to the newest RDNA, and we are also we also are willing to support the next generation. So luckily, the AMD instruction set architecture doesn't change much between generations, so it's actually not too much overhead to support all the oldest generations as well as the newest one in the same compiler infrastructure. We also constantly adding new optimizations. So, for example, Timur wrote a post-register allocation optimizer pass that does optimizations which can only be applied after already knowing which registers some instruction use. Also, currently the pre-register allocation optimization, so that is for algebraic optimizations, is being reworked by Georg. And then with the RDNA architecture, now the LU instructions they are pipelined, and in instruction level parallelism suddenly matters. This wasn't the case before. So we also wrote an ILP scheduler, so a scheduler for instruction level parallelism. And there, for example, for this just-in-time compilation, so compile times are really important, and we don't really want to spend time building an entire dependency graph of all instructions. This scheduler works by only looking at a small window of 16 instructions at a time, which greatly reduces the time necessary to reschedule the instructions. We also use the same scheduling framework for the so-called FOBD instructions. These are some kind of VLIW, so very large instruction word instructions, which can issue 2 LU instructions at a time. And we use that framework to combine multiple 2 LU instructions into a single ones, also in the same scheduling framework. So we also did some rework of the pre-register allocation scheduler, because I think scheduling is actually one of the optimizations which can provide the biggest benefits in compilation. So there's always some effort that we try to put into that. Also, there's a lot of other stuff that's going on in Akko. So this is an incomplete list of other things that we are doing, and I'm not sure I'll go over all of these. But just so you can see that, this is some of the features that we added. So new ray tracing formats, new shader stages for mesh shading, cooperative matrix instructions, and so on. So then for FSR4 in particular, there was a combined effort, so initialized by the Linux Gaming Discord group, and to reverse engineer the DirectX FSR shaders or instructions that are being used. So thanks to Hans Christian for that. And on the driver side, Georg Lehmann did most of the work implementing the necessary instructions and also doing countless optimizations, which were done in collaboration between the VKD3D side and Radv. So now it actually does work with quite good performance, and not even on the not only on the newest generations, but also on I think on RadeonSI now. So our team also contributes to NeuroCore. So this is the shared compiler framework between many drivers of Mesa. And so not going into too much details there, but at the same time, of course, we're also benefiting hugely from other drivers contributing to near core, and I think it's a really great example of how with open source development we can benefit from each other's ideas and contributions. So now going a bit back to, not sure what was the next. Yeah, okay. To how we refactored some of the compiler stuff. So how most of the current and newer drivers in Mesa work is that they do most of the work in NIR and very little in the back end. And originally when we developed Echo, we basically did the opposite. We just passed the NIR as it was to the back end and did essentially all the lowering from very generic NIR instructions to a long sequence of hardware instructions in the back end. And now in the last time we tried to go more and more into the direction of also doing the work in NIR, and this was so for once it was necessary to decouple the driver from Vulkan and make it also available for RadeonSI, but it also simplifies greatly the backend. So we don't have very long lowering code in the backend anymore, but have it in a single place. And yeah, and this includes most of the I/O intrinsics, memory stuff, memory accesses, and now we only have a handful of intrinsics that the backend sees, and it's yeah. So there's now a lot of NIR files in the common code, which handle the lowering of the different Vulkan specifics and also OpenGL specifics to very close to the backend instructions. Yeah, just this extends a lot of to a lot of different things. So, do you want to cover that? Okay. So yeah, Timur will explain what we learned from all this. Yeah, I mean.
Did we actually learn anything from all of this? Well, one of the things we learned is that the way we can develop Mesa more or less, I'd say, independently or individually, I think it's a good approach because it lets developers make choices.
Yeah, if you think of something like coming up with a whole new compiler backend when there is already something. It was a bet, but it was taken by the developers, and I think it's good to have like a lot of freedom in the choices that we can make, and so that we can like try to find a technically good solution. Yeah.
The other lesson is the more we can do in common code, the better. Simply because it reduces the amount of code that we have to maintain, not just us, but basically for everyone. So from the improvements that we did, both AMD drivers benefit, but not only that, but also for the stuff that we put in their core, all the Mesa drivers benefit. And the other interesting thing is that if you're using an older GPU from 5 years ago or 10 years ago, that is still going to benefit from the improvements that we are doing today, even if we don't enable all new features on the old GPUs. They can still benefit from like algebraic optimizations and stuff like that. So for anyone who actually wants to see all of this code that we're talking about, you can find it in Mesa, in here. And let's go back to the actual question that we asked in the title of the presentation. Are we there yet? Did we reach our goal? Did we complete our mission? So I think that Linux can be good for gaming. It's a good platform for gaming. But I guess the question should be determined by you guys. So I think it's up to you to judge. Are we there yet? What do you think? In case you think we aren't, you can help. So thanks everybody for listening. I hope it was useful. And do you guys have any questions? Any suggestions?
I don't know if this was a stated goal, but given that you've gotten AMD to delete the open source driver, I think that counts as success.
Do you plan to use more Vulkan common code in Radv? Also, what does ACO mean?
ACO stands for AMD compiler. I guess we graphics people are really bad at naming things. To answer your question, yes, definitely. And oftentimes, either we do it ourselves or we get merge requests from other people. So yes, it's on the long list of things that we want to do. So, but also if you want to help, you're welcome to.
Jetzt? Jetzt. Yeah, one thing that you didn't mention is that the German PC hardware magazine recently tested Radv in the Steam OS installation against Windows 11 on a handheld, and Radv even beats out the heck of the Windows drivers. So you're definitely absolutely competitive.
I guess that helps answer the question.
Hello. I just wanted to know, you mentioned a lot that at the beginning that AMD collaborates a lot with you to develop Radv, but then for FSR4 you mentioned that you had to do a lot of reverse engineering. Can you explain why that was the case?
No. So there is. So for FSR3 and older, so the games shipped with the actual shaders. So there isn't much reverse engineering to do. And for FSR4, let's just say that DirectX has no cooperative matrix instructions. So what the shaders do instead is some convoluted mess to tell the driver that they are now issuing a cooperative matrix instruction, and by basically performing an atomic addition to some weird memory location. And this isn't entirely obvious if you read the code. So there is some reverse engineering to be done to detect that. And yeah, this was mostly done by Hans Christian. And now the VKD3D translation layer translates these instructions to cooperative matrix instructions. So on the Vulkan driver, it just looks like a pretty normal matrix instructions in the end.
Hi, I just wanted to thank both of you and also everybody in the open source community for making Linux a gaming platform. So thank you very much. And you alluded to, but my question is, you alluded to it a little bit in the presentation, but what are some other big things that y'all plan on working on for AMD? Are there any big feature sets that are missing, or?
Well, the work never stops because there is always new hardware coming. There is always new Vulkan extensions coming. There is always one more instruction in the instruction set that you want to support, but it's just not there yet, or maybe it's missing from their core, or maybe it's just not that useful after all. So there is just a lot of tiny, tiny details. And there is also a list of major features. So like one of them was mentioned, I think, in Face Talk a couple of days ago. So that's going to also have day one support from Radv. Basically that.
Yeah, so I can probably explain more what the FSR thing is since I did that stuff. Basic idea is that FSR3 just calls into a magic DLL on Windows and it replaces function pointers, which then creates a compute shader that uses, so D3D doesn't have an extension model at all, so you cannot have SPARV extensions. So the way they do it is you just encode instructions that look like gibberish and they mean something to the driver. So the work was just to figure out what it means, create tests that expose all the things that it does, which turns out to just be plain cooperative matrix. But yeah, on the Vulkan side, it just looks like a normal, nice shader. But for this to work, a user would need to ship the AMD's proprietary blob FSR4 DLL. But then it somehow works, and we made it fast. So that's cool.
Nice work.
So you were mentioning that ACO can be used in OpenGL or in the OpenGL driver now. How does it actually stack up to the normal OpenGL driver? And also, how does it stack up against Radv running on Zinc?
What do you mean by normal OpenGL driver?
Sorry, the normal OpenGL compiler is what I mean. Because that's still included in Mesa, right?
So we're not normal. Okay. Well, so your question basically, if I understand correctly, is how do we compare with the LLVM-based compiler? And the answer is that it's actually a bit more pessimistic, like not as good as the results that we had on Vulkan, which is why the developers of that driver, they are a bit cautious about enabling it by default. I think for now, it helps them a lot with supporting older generations that are slowly getting deprecated in LLVM, or maybe were never really working well in the first place. Of course, you can enable it on the newer ones, but the question is just that they need to validate that it works well enough for the stuff that they want to work, and then they can flip the switch to enable it by default.
I think the long answer short, it's a bit of a give one, get one. So every compiler runs sometimes into the corner cases where it performs better or worse than the other. But there isn't as clear as a winner as of now.
Any more questions?
Regarding the testing, I know you had some CI with traces, but are you actually using it?
Sorry, can you repeat the question?
I know you had CI which tested Radv on game traces, but are you actually using it at the moment?
I think that's a question for Martin, the person sitting behind you. I know we have that feature, but I don't know when they are going to enable that by default. Like, I don't think that it's a good idea for pre-merge, but we don't know yet, really. We don't have like a specific plan. But Martin could give you like a better answer.
So you, so you don't test like routinely on game traces and so on.
So the issue with trace-based testing is that you render basically the same image, but maybe you optimize an algebraic instruction, and then you get a different floating point value, which is the same, but not exactly the same. So you get the same image, which if you look at it with your eyes, you cannot tell the difference, but it's not the same. So it's very hard to verify that in an automated way without somebody having to look through it. And basically that is the main issue with trace-based testing.
Yeah, but how do you know that your changes are actually working properly?
We run the full Vulkan CTS, and we trust the great developers working on the Vulkan CTS.
I see.
It has more than 1 million test cases at the moment.
Well, so I guess it catches more issues for you than for us on Turnip, because we found like a lot of things just slip through the CTS.
Yeah, the trick is to submit a bug to the CTS when you have that, so they can add a test to cover that for you.
Yeah.
We also trust your users to do trace testing by playing games and reporting bugs.
So AMD GPUs come with video encoders and decoders, and Vulkan has Vulkan Video to support that. Is it something that you currently support, or do you have plans to do so?
Yes, we currently support it, and we have plans to continue to support it. So there is actually a few people who are not directly working with us, but they are working on Vulkan Video specifically. And I think their name was on one of the first slides. And I think they are doing good work, so I think it works well, unless you know otherwise.
Testing, yeah. So from a testing point of view, like we have a lot of users playing games all the time, and when stuff breaks, you hear about it immediately. So that kind of helps.
If there are no more questions, thank you guys for coming. Thank you guys for listening.
Thanks.